Alright, today we're going over problem 7.33 from your homework. 7.33 is a two-step problem. First, you need to calculate the DC biases, and then you need to calculate the small signal analysis. So first thing first, we have the diagram right here. And you notice there are these big capacitors that say they have a capacitance of infinite. And so all we do here is for DC analysis, we pretty much just open up these capacitors and ignore everything outside of them. And for small signal analysis, we close the capacitors and we say that they're all shorted out and we just treat them like wires. And so part A, we need to make sure all the DC biasing is what we'd expect to be. We want it in saturation. And we have these values here, VT, KN, and VA. So we start off, let's just draw out what it will look like. So VG is pretty easy to find. It's just a basic voltage divider, 15 volts over 15 mega ohms over the last 5. So it's 15 times 5 divided by 15, just 5 volts. So VG equals 5 volts. To find VD and VS, though, is a little bit trickier. So what we're going to do is we're going to assume that the transistor is under saturation. So we're going to say ID equals Kn over 2 times VGS minus V threshold squared. And so we're assuming this is under saturation, and we're going to have to go back and test to make sure it's under saturation after we find these values. So assuming this, we can get values for VD of equal to 15 volts minus ID times 16 kilo ohms, and VS equals 7 kilo ohms times ID. VGS is just equal to VG minus VS, so 5 volts minus 7K ID. Plug this in here, square it out, you get a parabolic equation, quadratic equation, you can either solve this out by hand or use your calculator to solve. It's just the quadratic formula, and you get ID is equal to either 6.53 times 10 to the negative 4th amps or 5 times 10 to the negative 4th amps. And so we need to test both of these and see what values we'd get for voltages if we used them. So if we use the 6.53 one first, and we plug that in to VS here, we'll do 7,000 times 6.53 times 10 to the negative 4th. We'll get 4.571 volts for VS. That means our VGS is going to be less than 0.5 volts. That's less than our V threshold, which means this is in cutoff region. Obviously not saturation. If we try the next one, 5, so 6.53, you'll see we get a much nicer value of 3.5 volts. 3.5 volts gives us a VGS of 1.5 volts, which is greater than our VT. So we're going with this one. ID equals 0.5 milliamps. And if you check, that's what the book predicted, because the book has the answers. So that gives us a VG of 5 volts that we already calculated up here. That gives us a VD of 0.5 milliamps times 16K is 8. 15 minus 8 is 7 volts. This is also what the book predicted. And that gives us a VS of 3.5 volts. VGS of 1.5 volts. And if we can check to make sure that this isn't saturation by doing VDS, which is 7 minus 3.5, so 3.5, and make sure that's greater than VGS minus threshold. So 3.5 is greater than 1.5 minus 1, so we are in saturation. So now that we have all this, we can go and start working on B. So part B wants us to find GM and R naught. And those two are easy to find because GM is just 2 ID over V over. And so that's equal to 2 times 0.5 times 10 to the third divided by V over, which is just 0.5. And that gives us two millisiemens. R naught is VA, it's a V, over ID. And so that's 100 volts divided by 0.5 times 10 to the negative third equals 200 kilo ohms. And so that's that for part B. Part C wants us to do the small signal analysis. So now we're shorting all these caps up here, right? Just drawing lines through them. So that means this resistor goes away, and yeah, this resistor goes away, and we get this resistor tied in. So if you remember from small signal analysis, all DC sources are considered ground. So we're going to start over here. We get our V sig in here. With our R sig right here. Here's our 5 mega ohm resistor. Here's our 10 mega ohm resistor. Notice they're in parallel now because this is going from VG to VDD, which is ground in small signal analysis. VS is now just ground. We have a current driver that's a function of GM, VGS. This resistor is R0. VD goes to V out. But there's also two resistances of 16 kilo ohms that are tied to ground. Because remember, up here, this is ground, and this is ground. Oops, was I off the page? This is our current driver. This is our out. These are essentially our load resistors here. So there's that. Now we want to find a bunch of things about this. So let's start off with Rin. So Rin is always equal to Vin over In. In this case, our Vin is our V sig right here. And our In is the current flowing through V sig. So to get the current flowing through V sig, we do In equals V sig over the total resistance on this branch, which is R sig plus 5 mega ohm in parallel with 10 mega ohm. And if you notice, if you rearrange this, you get Rn is equal to R sig plus 5 mega ohm in parallel with 10 mega ohm, which is equal to 4 mega ohm. So now we want to find the gain. And so we're going to start from V out and kind of work our way backwards. So let's start off with calculating the full load resistor. So let's call that RL prime. That's going to equal R out in parallel with 16K in parallel with 16K. That's going to equal 7.7 kilo ohms. So we got a current here, we got one resistor here because we combined all of these. And so V out is just negative GM VGS RL prime. And so V out over VGS equals negative GM RL. This is most of the forms that this equation will take. It's almost always going to be your GM, your negative GM, times your total load resistance. So seeing that it looks like this, I know we're on the right track. So, and that's equal to 15.4, negative 15.4. Now we need to find VGS as a function of V sig. This is just a voltage divider. This is just VGS equals V sig 5 mega in parallel with 10 mega over Rin. Rn is just the total resistance that V sig sees. So VGS over V sig equals 5 mega, 10 mega over Rin. 5 mega in parallel with 10 mega is pretty big compared to what R sig is. This is like 3.8 mega. So it's no surprise that this comes out to about 0.95. The bigger these resistors are, the more Rsig gets passed to VGS. The smaller this Rsig is, the more Vsig gets passed to VGS. We want this to be as close to 1 as possible. So we want these resistors to be really big and this resistor to be small. Finally, we want V out over Vsig. That's simply equal to V out over VGS. G times VGS over Vsig. So negative 15.4 times 0.95 is negative 14.63. And so you see how we kind of go step by step through this problem. You start out with this big complicated mess up here, and then you simplify it to do biasing on it, DC biasing. And then you find the characteristics that let you do small signal, and then you do small signal on it, and that lets you know the gain in Rn. And later on, it will tell you the poles as well when there are capacitors in there.